Our course code is MCS1C04. It's a 4-credit course spanning 5 modules. What are the course objectives? Once you finish this course at the end of the semester, these objectives are to be met. The art of designing algorithms and flowcharts. We have to learn this. To introduce the concept of algorithmic approach for solving real-life problems. To develop competencies for the design and coding of computer programs. To learn designing programs using C programming language. You can Google for research papers on introductory programming courses. See, research is going on in every topic. Education is a major area of research, and how to apply the educational principles, especially in programming classes, is a big debate now. How practical sessions can be evaluated, say, especially in online. So the research conducted in major universities regarding introductory programming courses had a great result. See, in major universities, even non-computer science students can join for an introductory programming course. They have this choice-based credit system in true sense in foreign universities. Any student can join any course offered in the institution, cutting across the departments. Here, we don't have such a provision even till today. In that case, the research gave a lot of insights. One insight was an introductory programming course tend to focus on the programming language, not on the methodology for writing programs. That was the first comment. Emphasis is given on teaching the language, how to use the language for solving a problem. That aspect is missing. So first comment was that. Secondly, non-major computer science student, that means a BSc students, he or she takes up a course on introductory programming for out of sheer interest, but she feels that since this programming class was really a harsh experience for her or him, he doesn't want to come back to a computer science class after that. Even that happened. So educators took this issue seriously. Computer science bodies like Association for Computing Machinery, ACM, and IEEE, they sat together, and even they have prepared curricula. How to teach programming, introductory programming, that's a topic now. And they have come with model curricula. NPTEL offers courses on this. They offer to UG and PG students. Still that course is open. So a lot of efforts are still undergoing to make this meticulous. So don't feel that you learn something you have learned. Every time when we see something, there should be something to learn. So the ability to correlate whatever we know to arrive at new patterns is specific to humans. We have to make use of that. So you forget about whatever you don't. If I say forgetting means you have to remember whenever we hear about programming, you should know what you have learned in this course, how it is going to be applied, how we approach this course. That is very crucial. Now, see what are the outcomes of this course. At the end of this course, the learner will be able to understand problem solving using flowcharts and algorithms. Learners should also develop flowcharts and algorithms for problems using sequence, selection, and iterative constructs, three fundamental constructs of programming. And after designing the programs, learners should be also able to implement correct solutions. Here, I will say about one more aspect, separation of concerns. See, every problem can have different versions. Once I discuss a solution, an immediate alternative can come into your mind. In this course, our concern will be separated from efficiency and correctness. We will see whether we can form a correct solution for a problem. Efficiency comes later. You have a separate course called as analysis and algorithm analysis, say in the second semester, where you will learn how to measure the efficiency of a solution, how to classify problems into several categories. All these things you learn in the second semester. In theory of computation, in the first semester also, you will be able to classify solutions, several classes, and how can you deal all these type of algorithms and solutions, that also you will learn in the second semester. It's in the course is designed in a logical order. See, this is our syllabus, an overview of our syllabus, what's happening. In unit 1, we will throw our weight on problem solving and problem design, introductory concepts. What is a problem? What are the basic steps in solving problems? How the problem solving process can be started? How to design a program? When you write a program, what are the things we have to take care? So all these things we'll discuss in unit 1. Unit 2 is about language preliminaries. Once you know how to design a solution, the solution will have to be implemented in the laboratory. For this, we need a tool. We have in this course, C language has been chosen as the vehicle for that. So just the preliminaries of C language will be discussed in unit 2. Our aim will be not to teach C, but the aim will be to relook into the problem solving capabilities that we have learned throughout our UG days. Unit 3 is about decision making, sequence, selection, and iteration, basic constructs. Selection is decision making. How decisions can be made in the problem solving aspect, and how to write solutions that include decision making aspects. We also know that there are several kinds of decision making statements. Say, for example, in C, we have if else, we have else if ladder, we have switch. But the thing is that, can we convert a simple if statement to switch and vice versa? This ability is also crucial as far as a programmer or designer of a problem is concerned. We should know the syntax and semantics of each of the decision-making constructs, and we should know how they can be used interchangeably. And in this unit, we'll discuss about that. Unit 4 is about iterative constructs, different kinds of iterative constructs. And again, as I discussed about, as I just mentioned about decision making, how different kinds of iterative constructs can be used and how interchangeably you can apply that. And there are some case studies also in this unit. So we'll go through them one by one once we visit unit 4. In unit 5, the concept of modularization, how to generate modules in a program and associated activities, how a module can be written, how modules can be implemented, how the blueprint for modules can be laid out to implement them. So this is the flow of the course. We can say that computer science is all about problem solving. That's it. This science was evolved just with that, the quench to see solutions for problems, right from our ancestors, ancient men. And more precisely, we can say that computer science is all about developing correct and efficient solutions. Efficiency and correctness. Why correctness and efficiency are underlined here? See, a program will be executed by a machine which can do anything in lightning speed. So whatever you instruct, it will be done. Even if you instruct something in a bad way, it will be done quickly. Machine does not have any ways to check the correctness of a solution. Once the solution is translated into a language in which it can understand, it will start executing that. So it is the designer's responsibility to see that the solution is correct. There can be several methods of developing solutions. The most efficient solution is to be delivered. Now, if we say efficiency, since you use your mobile devices, you will have several answers. A program should take less amount of space. A program should also take less amount of time, space efficiency and time efficiency. And these aspects also should be measured. After that, we will come with a problem solution. So the entire computer science field is centered around this my major area. Now, to be more specific, we can add one more sentence like this. Computer science is a scientific and practical approach to computation and its applications. We can also say that computer science is a science of abstraction. So how the things will be abstracted? The first part is representing a problem. You have to formulate what you have to do, the problem statement. And then we have to devise the appropriate techniques to solve it. And that part is called as design and analysis of algorithms. So these two are the fundamental aspects of problem solving, which a computer science graduate or undergraduate has to master these skills. Our bread lays here, my dear students. You may know n number of programming languages, but if we don't know how to design a correct solution for a problem, all our so-called skills will be under a big question mark. I repeat this, how to represent a problem and how to arrive at the mechanizing techniques to solve it. Suppose that if I ask you to say, write a solution to add two numbers. As a designer, we should have several questions now. Do I have to add integers? Do I have to worry about signed numbers? Do I have to worry about fractional numbers? See, based on the requirement, then you will arrive at the problem statement. Yes, I will do only this. And this is agreed upon by the customer also. Later when the customer comes and questions us, we'll show this agreement. See, I had told you that I'll be doing this and I have done that. If you want to do something extra, we can have a new agreement, pay for that, I'll do that. This is how development goes on. So developing a solution comes from creating a right model for a problem. Then once the problem statement is clear cut, the designer will think about solving it. Now, this issue can seem to be simple for us because we have written only simple type of programs in our programming assignments. But really, computer scientists are doing a lot of things to tackle this seemingly simple issue. They study in detail about the nature of problems, and they classify problems into computable problems and problems that are not computable. Yes, by dears, there are problems that cannot be solved. In such case, what we can do? If a problem can be solved, how can we say that a problem can be solved? A problem should be solved within using a finite amount of time. We cannot make the user wait forever in front of the machine. Customer will leave our program, he will restart the system, and he will never use that again. So how to see that a problem is computable and not computable? If a problem is not computable, then what we can do? We will develop heuristic solutions. Those solutions need not be optimal, but still there will be an answer for that.